the whole point of this is for pathologists to classify tubules and then generate a map with XY location as well as the category. So I'll load some cases. So what are the VIPR gated? Here's a good one, HRT. Let's do it by image so I can pick a good one. Let's see which is a good one. That's a good start. So basically, these are the previous gated tubules by Hale, where the original image is modified. So we just have the tubules, and then a pathologist can, by selecting the numbers, pick the class just automatically here, where you can click them. It's faster using the keypad though, and then basically just then go through various tubules and categorize them. And when you're done, so this and then this generates metadata files that get sent back to the aggregating group. But each group then can independently generate labeled images for ground truth mapping. If something's abnormal, for example, it puts, besides labeling the image itself, it generates XML and CSV files when you save the data, which then if I click on that, it just saves it as 2 files with timestamps, and then you're done. And that allows the pathologist then very quickly to generate the primary data needed for kappa statistics between multiple sites. So an example of building a tool to the need as opposed to having the tool be force fit on a group. And I think there are many cases where lightweight tools like these don't exist and should exist, just to speed up workflow. So it's a very mundane tool, but it allows for a very specific type of activity. And you can label things that you don't know what they are. Oh, the other thing is it's fully editable. So if I make a mistake and I right click on something, it just goes away and I can put a different category. So these are features that were driven by pathologist input and how the tool would be most workable. Because pathologists change their mind. So if that's, for example, unable to identify, you click 8, but then if you later decide you want to identify, you could put a 7 or go back to an 8. So and this tool, by the way, is part of KPMP. Anybody who wants this, I'm happy to share it.
So this is an image, it looked like a silver stain or something.
That's PAS.
PAS, okay. So, you had already pulled out the tubules with your Hale algorithm. And so you're basically asking the pathologist to confirm how well it did and also the different types of tubules.
Well, right, but we actually did, we did one additional thing. We did also the VIPR after Hale. Let me show one of those images. And we wanted to see how well the algorithm correlated. Let me get this running again. So those are the pathologist scores. But there's the share thing. There we go. There it is. So, but the output of the whole pipeline, which I didn't show you, looks like this. So VIPR basically then goes through the image, and this is entirely unsupervised classification, proximal, distal, or abnormal. And then so what we're trying to do is see with the pathologist scoring how it correlates to a completely unsupervised machine-based classification. So this is the Hale gating of the tubules followed by the VIPR classification of each tubule as a fully autonomous pipeline. And so we needed the tool to be able to compare what the fully autonomous pipeline did compared to a pathologist grade, if that makes sense. So this
No.
this is the full output of the pipeline that you didn't see. This is all these dots are unsupervised classification of the tubule.
Mhm.
And so we want to know what the pathologist thought, and then we generate a kappa statistic.
That's nice. So, you know, does that, I know with the Hale loop that Panaki's group talks about with the human AI loop, they, you know, the AI algorithm will provide some annotation and then the human can check that. And then it kind of goes back and initially there may be some human, you know, annotation, then it goes to the AI, and then it goes back to the human and then back to AI. And so it gets better and better as time goes.
Well, yeah, but the human AI loop, so this is done in partnership with Panaki. Let me share this slide. So initially what we have is just a renal biopsy. What Hale does by itself, and that loop is basically a deep learning iterative process by which the precision with which the different features get segmented get better and better. So in the case of Hale for kidney, it's identifying tubules, the interstitial fraction, the glomeruli, and the vascular spaces. And for the purpose of this pilot, we were just interested in tubules. So that interactive loop that Panaki talks about is refining the mesoscale to find the structures. That's all. Not to classify them, just to find them, which is itself is a significant feat. So we have, you know, after multiple iterations of the human interacting with the ground truth to train this. So this part, in fact, is semi-supervised and supervised until you end up with an autonomous pipeline, which we now have. So we use Hale at the mesoscale, the organ itself, to find the tubules, which are these light blue regions. Conversely, what VIPR does at baseline is it categorizes the biological context, as we've discussed previously, of every pixel. But it suffers from signal to noise in that when you're doing classification, you've got all the pixels in terms of classes that are not the thing of foreground of interest interfering with your foreground, in this case, tubules. So what we've done by combining these two algorithms, we take the original biopsy, we run it through the Hale lockdown. So this is now unsupervised because it's been optimized. We get the tubules, and then we will run VIPR on each region, which gives us a computationally equivalent of a bag of words. And then we do clustering, k-means or XGBoost, on each tubular region and find out what the biological context of the neighboring pixels in this region most closely fits. And that generates a class. And then that class is the final result. So this is a combination of Hale and VIPR that leads then to each region now being classified by VIPR as to, you know, its biological meaning. And you can arbitrarily pick any number of classes. So that's the purpose of the overall combined pipeline. And you can apply this, of course, to all structures, not just tubules. We're going to do it for glomeruli, for the vascular spaces and interstitial fraction. But we picked tubules as the first pass because it was the most numerous thing we can generate the largest N for any given renal biopsy, given that glomeruli are a little bit more rare in their frequency. So that's this. So in order to validate what these dots are, what the completely autonomous pipeline generated, we needed a collaborative tool for pathologists to share their grades or their assessment of each tubule, which, you know, is hundreds and hundreds of clicks across multiple tiles. And this lightweight tool allowed them to do that and send back tabular data. So that was the intent. And you can see we had this for literally hundreds of images. Let's see this. So we've done this for, so this is the original biopsy, the Hale gated biopsy. This is the pathologist classified, which has a number for each. And then the machine learning overall pipeline classified. And then we basically do an inner observer between computer here and pathologist here, generating our kappa statistic per class of tubule. And it turns out the numbers are really quite good. If you take normal tubule and abnormal and add them together, 87%, and actually with more pathologists, this went above 95%. And for distal versus normal, distal abnormal versus the machine graded, it was 88%, which up to 98% after we got multiple pathologists. So the tool is really quite good in its performance of recapitulating what a pathologist can do. So I'm encouraged that we can build eventually fully autonomous tools to not just identify the tubules, but then grade them or classify them, which is pretty exciting.
Yeah, and I suppose that you could do that as easily for other structures in the kidney than
Exactly,
tubules.
that's the plan. We're just starting with tubules.
Yeah.
The plan is to do this for tubules, then glomeruli, then vascular spaces, then interstitial space.
Yeah, fantastic. And this is beautiful. And this is indeed the way to confront the AI pipeline with the human pipeline, because otherwise, if you don't analyze the human pipeline in the same detail as the AI pipeline is working, you'll never have a good evaluation of the capacity statistics. So I agree with you. This is the way forward.
Exactly.
And is this implementable easily in other centers, or how does it work?
So it's a combination of Pinaki's Hail tool and our VIPR tool. The good news for both of those is the source code for those is fully controlled by each respective group. There's no proprietary commercial component, so there's no commercial encumbrances. So it's really an exercise in just wrapping the whole thing together and making it available. So, and the intent is not to commercialize this, but to make it available as a collaborative tool. So the only barrier really is the ability of individual sites to absorb the technical capacity, and or if we can get around liability issues, stand up a public repository that can be used by any number of academic sites just as a resource. And it gets a little bit tricky if it's being used clinically. So I think we can just have to navigate that, right, with validation and things like that. But there's no commercial encumbrances, which I think often is a barrier to adoption of these tools. At this point, it's just the technical barrier of deploying a pipeline locally, but it's not a money thing, it's a resource thing. There's no licensing involved or anything like that.
Yeah. In which language is this written?
Many. So the Hail pipeline is written in a combination of Java and some Node.js and some Python.
Mm-hmm.
And my code is a lot more monomorphic because I normalized it about 2 years ago, rewriting all of it. Because I wanted to be compatible with the enterprise's Windows-based architecture for workstations, I wrote it in C#, but it could very well be ported easily to Python or anything else. But right now it's an entirely monolithic solution in C#, which takes advantage of the Windows graphics primitives. But that's a very C-like language. So porting it to C, C++, or Java would not be that big a deal.
Yeah, sounds fantastic. Do you have a reference for that? Because I could look with our engineers whether they could see how they implement this, because I really believe that this kind of tools is what the field is needing urgently. And if you have it, it would be a little bit sad to have others developing something that is looking like it while not the same, and then again having more dispersion than congruence on the proceedings of the field.
Yes, we have several references and quite a few for the underlying architecture, which is SIVQ, and more VIPR papers will be coming out this quarter. We just submitted an abstract, actually, this is some of the data, to ASN yesterday. I don't know if you had the same deadline issues we did, but we got them in before 2 p.m.
Yeah, deadlines or for catching them, I agree, it's always difficult.
So yeah, I can send you some references. Happy to.
Yeah, but I'm watching the KPMP website, and actually what I see is that you have this is likely giving us the hints towards how we can get it. So I will first look at that. No need to send me anything.
Okay.
Thank you.
Yeah, because we don't have the source code for this on the KPMP website, but we have now a growing library of executables and things we can share. So
If you have that lined up, it would be fantastic if that could be shared, perhaps even in the Slack program for the whole
yeah, I mean,
working
I
group.
use Slack locally in my team. Is there a Slack for this group?
Yeah,
Yes.
yeah, in fact, I mean, I thought I had added you. Let me make sure.
Maybe I haven't accepted it. Let's see.
Let's see. Invitations, let's see.
So what I'm thinking, the recording from this meeting, I think it'd be good to put up just the second half, like starting with this stuff. I think that it would be really interesting to many people. So if you could send me the file,
Sure,
then
sure.
I
could do
can
that.
edit it to that point. I appreciate everything that happened in the first part. It's just a little tedious for everybody to wade through that. So I think the proper edit is to get to the meat, the intellectual meat of the conversation would be better. Yeah.
That's a good point. Yeah. Yeah, and yeah, I can definitely send you the video.
Yeah, I have sort of a strange life where, you know, video editing is like most of my days. So anyway, yeah.
Oh yeah, I tried to add you again and it said I had already added you. So
Okay.
I don't know that I got a notification. I'm in Slack right now. I don't see the group, which is
do you
weird.
do you have a maybe there's a I use the med.umich.edu. Let me see.
Oh,
if
I might have two. It might be just umich.edu.
see.
That could be the problem.
Let's see. Oh, okay. Yeah, I can try. Maybe. Yeah, I'll try to do that. And
The University of Michigan is strange in that although it's one email address, it's two different personas for third parties. So Slack doesn't see med.umich.edu is the same thing as umich.edu, if that makes any sense.
yeah, well, that was really great. And I think it could really speed up annotation because, you know, the problem with, you know, it's like, you know, the problem is it takes so long to do sort of the human annotation. I've done a lot of like circling of tubulitis and
Exactly. It's time consuming.
yeah, it is. It's very.
Yeah. And we can modify this tool to label other things in tubules. Tubules was just the first pass. So it's just, it was proof of concept. And for example, Laura Barasoni used this to label hundreds and hundreds of, probably thousands of tubules just in a couple hour period. And if she were to do this manually, it would have taken her days.
Oh yeah, yeah. That's amazing. That's really, that's really amazing. Yeah.
So any of you who doubt this can just directly, since I'm the author of the tool, I didn't use it as much. You can ask Charlie Alpers or Laura Barsoni what their experience was, because they've labeled thousands of tubules with this tool at this point.
So a question, what are you learning, or what do you think you will learn from this?
So I don't know if we're learning anything, but we're characterizing the level of performance of a fully autonomous pipeline for doing something just as mundane as saying proximal versus distal tubule, and then normal or abnormal. Got to start somewhere. So we wanted to start really modestly. So proximal versus distal, normal versus abnormal. So that's something a pathologist can do most of the time, but as you know, when there's really altered morphology, and just going by Lauer's opinion, there's many times you really can't say if it's proximal or distal. You just know it's abnormal, right? It's so distorted. And so the tool will do that too. So it really is incumbent on us to have nephropathologists generate their baseline scores and then generate kappa statistics between pathologists. So we know what the art of the possible is. And then kappa statistics between the average of the pathologists and what the pipeline generated. And that's where we're just really encouraged that the pipeline seems to be performing at the same level as pathologists.
Are there other sources of ground truth, other stains?
So that's a great question. And the answer is yes. We're in the process of negotiating with the KPMP tissue committee to get unstained sections to do aquaporin, for example, or other, using Codex and other tools that Zoltan has to do biological ground truth, so that we can compare both the pathologist scoring as well as the machine scoring to what it actually was, which is we need a standard candle of the absolute truth, which would be a biological immunological target, for example. So immunostaining, fluorescent staining.
Right.
And that hasn't been done yet. That's in the process of getting done.
That's awesome. Well, yeah.
And presumably with more stains, because Zoltan can do many stains. And in fact, we're working with Michael Eden, who can do the Visium transcriptomics. We'll have thousands of signatures from a transcriptomic perspective. The hope is that we can identify more subtle biological, morphologic subtle features that might be subvisual, but reproducibly present, that correlate with the transcriptomic signature, which is like a 2,500 degree vector. So there's so much work that needs to be done, combining the morphologic space with the genomic and other omic space. And we're starting to get the spatial data coming in now from KPMP, where we have not per pixel, because that's not what Visium does, but per 45 micron region, 2,500 genes, which is pretty amazing.
Wow. Huh. What technology are they using for that?
Visium.
Okay.
And the Visium is about to, it's being prototyped a number of places. We're about to get it to go down to, I think it's 5 or 7 microns.
Wow. That's, yeah. I know
So that'll be, at that point, it'll be true single cell analysis.
wow. That's interesting. Yeah. I know a lot of people are using like near single cell, like nanostring DSP or 10x
Exactly.
genomics, and yeah, but that's really great. That's going to create a lot of data for people to.
It already is. I mean,
Yeah.
if you go, and a lot of the data on the KPMP website is publicly available even without a data use agreement. And the rest of it is available with a data use agreement. And it is, at this point, it's getting to be a fraction of a petabyte of primary data. So there's a ton of information that can be extracted from KPMP right now.
Wow.
On over 100 participants. And
It's-
they're a blend of chronic kidney disease and acute kidney injury. And what we're seeing in the signature is acute kidney disease, and I guess you knew that as a nepropathologist, really kind of smoothly transitions into CKD. It's a spectrum. It's not A and B. It's like, it's different trajectories from acute injury leading into chronic illness or resolving into recovery. But we're finding even at the molecular level, the recovery is not actually recovery. It's a shift from the baseline molecular fingerprint that in some cases is permanent, which we hypothesize leaves the patient at a more susceptible state for subsequent bouts of injury. So that they have initial resilience, you take another hit, and then their kidney's not going to come back like it did the first time.
Huh.
At least for podocytes.
that's really cool. And I mean, and that you have a lot of metadata too, like and very, I think it's carefully designed as far as like,
Yeah, there's a lot
APMP.
of clinical, there's lab data,
Yeah.
there's a clinical notes, the charts, there's so much metadata, it's kind of just overwhelming how you would most effectively use it. And some of that metadata is time series, which
Yeah.
lets you track, evolution of process of disease. So, I mean, it's going to take really, really good data scientists to figure out how to maximally leverage that data. It's a very rich set.
Well, Maarten does really great work that way. His I really admire his papers like that in that regard. Yeah.
Yeah, so it's a trove of data to be mined.
So let me just circle back. I need to leave like real soon now, but just to get your sort of global sense of the federated learning world and whether this is something that's going to work or not.
Yeah, I mean, I think, yeah, it eventually will. I think we definitely should think about how to do that. And it sounds like, you'll actually, his solutions could have that component too. So I think different people's solutions are going to have a federated component.
Okay.
Yeah, before you joined, Richard, I just commented that I think it's important though, that the tool doesn't drive the process, that there's a need and then you build tools towards the need as opposed to having tools and you try shaping the need to what the tool provides. So if you have a federated learning need to collaboratively do something, the solution should be based on what the collaborative need is and not vice versa.
Got it. Of course, for people without a lot of time or resources, it's nice just to say, oh, we're going to use X.
Right. And that's convenient, but if X serves the need, that's great.
Mhm.
But if X doesn't quite serve the need, now you've got this kind of crazy hokey workflow where you're trying to force fit what you really need into the wrong tool. And
Right.
that's not good either.
Yeah. And I think, the way you have open source tools is really, I mean,
Yeah, so you change
Yeah.
them to fit the need. Exactly.
yeah, I think that's the way to go. Well, I think, in 4 weeks will be our next meeting and we'll have a lot of opportunity to talk, especially with the Amsterdam group with Mikey and Hermsen and Dominique van Midden and Joran. And, they're going to have this solution that people can test their algorithms on. So I think that's going to stimulate a lot of conversation, and hopefully we're going to learn how the BAMF group can get involved in that. And we can start advertising it on Slack and things like that for groups to get involved and maybe even test their solutions on their bank. So I think that'll be great. Does anybody else have any last comments, or because I'm sure everyone's really busy.
No, I think it's been a really good meeting, and it will be valuable to the people who aren't here to see the exciting things shown.
Yeah, and I have to say that the Slack channel is always good to catch up with the meeting afterwards. And so I don't
good.
know how many people do that, but I try to look at and to rewatch, even if I agree, like in the beginning, sometimes there's some introductory discussions, but in the end, it's always interesting to get the important pieces of the discussion. So thank you for putting all of this on Slack. I believe many people benefit from that.
Yeah, I'll try to be more faithful. I think there are a couple of meetings I probably didn't put the video on, but those are probably the ones that Kim put on YouTube. And so what I need to do is I need to go back and organize that. And we have tons of videos, and there's some that we haven't been able to put because some people presented their like stuff they want to publish. And so I've tried to respect that too. But later on they might let us know that we can post it, and we'll do that too. So yeah, well, I appreciate your saying that, and I'll try to be more faithful about posting on there. That's really great. Well, yeah, well, thank you all so much. I hope you, if you're going to ATC, maybe I'll see you there. And
Yeah.
if not, I look forward to seeing you in about a month on this or somewhere else. And I really appreciate your participation. Yeah.
Right.
Thank
Okay.
you very much.
Okay.
Great.
Well, take care. Thanks a lot.
Thanks. Yep,
Take care.
great call.
Thank you.